Welcome back to another design patterns video. In the last video, we talked about strategy pattern. And in the comment section of that video, some of you mentioned that the example that I used in the video was sort of too simple, like too many ducks and so forth. And I think that's a very good point. So it might be tricky to sort of realize how the strategy pattern would be applicable in any sort of real world context if I'm not actually providing anything that's sort of more sensible, that sort of looks like anything that resembles a real world context. So that's what I want to spend this video on. Essentially, we're going to talk about the strategy pattern. We're going to implement it again, but we're going to implement it in something that very much more looks like an application, right? Or like a piece of an application or a context that could be part of an application. So for context, what I do is that I'm a PhD student and my research method is essentially simulation. And this in some sense has nothing to do with simulation, but I'm going to take an example from that. So I mean, when I thought about the strategy pattern, this example immediately came to mind because the other day I used, well, what we're going to look at, but in a piece of Ruby code that I kind of sort of just quickly hacked up. And I remember now, this is what I talked about in the other video as well in the end, but we didn't actually look at any of the code. So I talked about how, like, even if I'm writing something which is very simple, I try to make sure to maintain a sufficiently high level of abstraction so that I'm not gonna paint myself into a corner where if I suddenly want to make a particular design decision, it's not very expensive to do so. Like, because when you're just hacking something up, I think speed is one of the most important things, right? It's like you have this idea and then you want to minimize the time it takes you to move from your idea into an actually working solution. And by maintaining some particularly high, that makes no sense. What I mean is a sufficiently high level of abstraction, it's easier to move in any particular, or any direction, right? Faster. But anyways, now I'm drailing off topic. What I wanted to say is that I used, so first I thought I would show you the Ruby code, but then I figured since this series is actually in C#, let's just re-implement something that looks like that in C#. And it's, I mean, now I'm painting this big picture, but actually it's super common. Like, again, like as we talked about last time, strategy pattern is everywhere. Like dependency injection is everywhere. So yeah, I think we'll just jump into it. But before we do that, let me just also mention that if this is the first video that you're jumping into in this series, what we're doing is in this series is that this is a screencast series where we talk about object-oriented design patterns, and we're using C# as an example language. But don't worry if you use Java, because they're essentially the same language. And I mean, if you're using a dynamic language, again, like don't worry, like Ruby or Python, don't worry. Just remember that it's roughly the same, but you don't have the types. So if you don't have the types, you use duck typing, so then you tend to just not explicitly specify the interfaces. But most of the design patterns, like maybe with the exception of a visitor pattern, because visitor pattern doesn't look exactly the same in a dynamic language, but in a dynamically typed language, most of the patterns look exactly the same. You just omit the interfaces, right? This is a separate discussion. Let me know if you want us to dig more into that discussion, and maybe we can try to figure out some format of doing that. But anyways, what I wanted to say is that if this is the first video in this series, that's what we're doing in this series. And if you're more interested in sort of the high-level discussion around design patterns and want to have a look at the UML and so forth, then I would highly recommend my fairly popular whiteboard series. That's more like a lecture series on design patterns. The link is in the description. So definitely, I think this is sort of a supporting material to that series, which is sort of a bigger picture introduction to design patterns. Anyways, let's now get into it, okay? So we are here in the terminal. I have this empty folder. There's nothing in it. We're just going to keep this simple and jump into Vim, right? And just like last time, we're just going to say that let's create this program file, and let's say that we have a class called a program, and then that there's a public static void main entry point of the application, right? And then let's just say console write line hello world, just to make sure that we're sort of wired up correctly. And in order to have a console, we need to be using a system, right? So that's that. And then let me just map a keystroke to, what is that? MCS of program.cs, right? I think that's the way we compile it. And then map another keystroke to running the exe file that will be produced. Let's just see if we can compile. We can compile, and then I'll hit the keystroke for running. We can run, and then you can see here we get the hello world output. Okay, so now we're wired up, right? We just have some way of working with this. So a bit of context, right, in order to build up this example. So what I built, this Ruby application that I talked about, I can put a link if anybody's interested, but just ask and I'll put a link to the GitHub repository. But it's a messy bit of a code, so yeah, don't make too much of it. But anyways, it's a Monte Carlo simulation, and what a Monte Carlo simulation is not really relevant for this particular video. But what we do is essentially that you have some input configuration, and then from that input configuration, or rather you have a distribution of a number of variables. You sample these distributions, and then you do some computation on that, right? Or we do some computation on that. Point being that there's essentially, we run the same program tons and tons of times, like 100,000 times, right? And then we compute what the output would be in a number of different random why am I not making any sense? What I mean is that we have a number of different input variables, but instead of just having concrete input variables like x is 5 or y is 10, right? It's like x is a uniform distribution between 0 and 200, so it could have any of those values. So, and then we just run the simulation multiple times, and for every time that we run the simulation, x will have a different value. So like in one world, x will be 1, in another world, x will be 100, in another world, x will be 5, and so forth. And because there are lots of different variables that are interacting, it's difficult to it's unnecessarily difficult to construct an analytical solution for figuring out how these different variables interact, and then hence sort of predict what the output will be under different configurations of input, because we have lots and lots of input variables. Anyways, that's irrelevant for now, so don't worry if that isn't making any sense. What I want to say is that we have a program that spits out lots of, let's say, rows, quotation marks, of output, and we then want to be able to compute statistics over this output. But I take this output, I'll just spit this output into a CSV file, and then I'll take that output and feed it into R, right? So that's a different problem. It's not a concern of this program. But we're just going to do something very simple, right? We're just going to say, like, let's say that there's a class called simulation, right? And let's say that there's a void method where we can say run, let's say. And probably we would do some, I actually have some cheat notes. Let me just check this. So I'm going to say something like, yeah, okay, so what does run do? I mean, what we want to do, let's say we're just building something like a coin flipper, right? So we want to say flip a coin and return heads 50% of the time and tails 50% of the time, right? Tails 50% of the time, blah, 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 blah. So how would we do that? We would do something like, well, we need to have a randomizer, right? So so let's just say there's an R&D, which is a new random. So we're instantiating the random class, and then we would say something like this.rnd.next, next double, and that gives us a number between 0 and 1, right? So it gives us like 0 and 1, if I'm getting that syntax right. Like we can't get 1, but we can't get 0, and it's like as many decimals as we can have, I assume, right? It's not relevant to here. So if that number is less or equal than 0.5, then that means we should return heads, let's say, and if not, then we should return tails. Okay, so and now we could just return, but we're not actually interested in returning that. So let's say we want to print that to screen. So let's say this is the return value. So we'll just say console write line, and we'll just write this. Actually, maybe we'll do this. We'll break this out. So we'll say result, and then we'll say, oh, sorry, now I've been doing JavaScript too much. String result equals this stuff, right? That's the run method, and then we have a random here, and this is a class. Okay, fine. Let's just see if this compiles. Does not contain next. Oh, so it's not called next. Let me. Oh, sorry. Of course. Capitalization. So the standard in C# is that all of the first letters are uppercase. This is the problem of switching between languages all the time. So that compiles, right? That's fine. Okay. So this we can remove. So that's running, right? But this is of course one world, quotation marks, because this is one sample. So what we actually want to do is, I'm just gonna hack this. I mean, probably you would want to have a different class for every world instead of saying, so what I'm gonna do is I'm gonna do a for loop here where we say, okay, from 0 until I is, let's say 100, actually let's say 10, and then I++, and then we're just going to do this that many times, right? So probably you would want another class here, but I'm going to skip that for now just in order to keep it simple. And if we feel like we feel a need to extract that, then we'll extract that in just a moment. But let's start here, right? So now if we ran that, that still compiles. Of course, we're not outputting anything. So instead of doing this stuff, right? Let's say that we did, let's say, so we say simulation, sim equals new simulation, and sim.run, right? That compiles, and then let's run that, and we'll see, okay, we get tails, and then heads, and then tails, heads, heads, right? And if we run that again, you can see it's not the same series. So this, whoops, this seems to be random, right? We get different series all the time. Now, of course, okay, here's the thing. So I jumped into this for loop immediately, but let's forget about this for loop. Let's say that we just had one output here, like this, okay? Console, right? What did I, wait, well, oh, I accidentally inserted all of this stuff here. Yeah, okay, never mind, okay. Compile, it compiles, and then let's run. Okay, now we only get one output. Notice how, okay, heads, tails, heads, tails, and so forth, right? We only get a single output. But the point was that we want to have multiple different worlds. Now, the thing I'm looking for here, right? The reason that we would use strategy pattern here is that what I'm aiming for is that this console write line that we've put here is sort of hard-coded, right? We've hard-coded the idea of printing to the UI or printing to the console, actually, like concretely printing to the console, We've coupled that idea into the idea of having a simulation that performs this particular work, right? Which is in some sense like the business logic, if you think about it, right? Like this is literally the business logic. You don't want to mix printing with business logic, right? Because printing has nothing to do with our actual business logic. Our simulation could care nothing about, like this is a heads-tails simulation. It's just a coin flipper, right? It doesn't care anything about whether we want to print to the screen or not. It just wants to flip coins. So that's the goal here. Now, of course, if we only had one scenario, we could just say that this is not a void method, that this thing returns a string, and then we just return the result like this, right? And that's fine, right? If we compile, that works, and if we run, we now get nothing, okay? Because we're not actually console logging anything, because then we would say, okay, string output, or sorry, result was the word we used, is the variable result contains whatever we get when we run sim.run or simulation.run, right? And then we could say console write line result. Okay, now of course that works perfectly fine. The issue is that we don't have this. We actually have multiple ones. So then you might say, okay, but no worries. We could just go back to this thing for int I from 0 until let's say 10, and then I++, and then we'll just run it multiple times. And instead of, so we'll say we'll have a list results is a new list of string, right? And then we'll just say results.add instead of equals, right? So delete up to equals like this, and then we'll just return the results instead, right? And to do this, we need to have system.collections.generic, I think is what we need, right? Let's try this. And that doesn't compile. Generic list t, oh sorry, because here we of course need to say list of string. That, okay, cannot compile, oh sorry, of course, because our return type is string, but we want to return something which is of I collection string. We want to return a collection of strings essentially. And then this is of course a list of, or I mean we could just say an I collection of string, right? That's our result. So this should actually be results and then results, but let's say result here. Now that's compiled, and if we run that, you can see, okay, what we're printing now is a list, because in order to print that, we of course need to do something like for each string s in result, and then we just console log this string instead. So sorry, I'm moving a bit fast because we're not going to care about this, because I just want to show you the problems of this particular approach in this particular scenario that I was in with the simulation, right? So now you can see, okay, this works fine, no problem. We are instead of directly printing from this run method of the simulation, which clearly is a bad thing, what we're doing instead is that we're just running, producing this list in memory, and then returning that collection. And then we just, okay, for each, and then we console log or console write line outside of that. The issue with this is that we have something like conservatively 100,000 runs, right? We might actually want to run like 1 million runs. So when we're running these simulations, it's not an issue if it takes like an hour to run the program. That's not a problem. The problem, however, is that any particular output, now, I mean, here our output is just heads or tails, right? But the output that we have from that simulation might actually be pretty large, like memory-wise. So we might actually run out of memory if we try to build up a collection of all the output and then take all that like massive output and try to dump that output into a file. Like, it's possible that we might not even be able to construct that thing in memory, at least not efficiently. That's one way of thinking about it. Another way of thinking about it is that it's if for some reason the program crashes meanwhile, while running, like let's say we have a simulation that takes a day to run, like if it crashes, I want to have the intermediate output. I don't want it to crash and then it's like, oh, okay, I have to fix this bug that, I mean, clearly there shouldn't be a bug, but I have to fix this bug now, and all of this time that I've waited, like half a day, is pointless because I have no output data left. Like the program crashed and there was nothing written to file. So I wanted to run to file, I wanted to write to file while running the program, right? At the same while it runs the program, so that at any point in time I can just cancel, I can just kill the script, and we have output for however far we got, right? Like, I mean, even if I tell it to run like 1 million times and we only get to 100, and I'll stop it, at least we have 100 lines of output or 100 worlds of output, right? Which is a good thing in this particular scenario. So that's why this is not a sensible way of doing it in this particular case. Now, of course, you could use something like the iterator pattern and then yield or something like that. So that's surely that is surely an option. For sure, that is surely an option. We're going to do something slightly different, and I think this is probably pretty sensible in this particular scenario, especially like if we're thinking about this in a strictly, let's say, object-oriented paradigm. Like we're thinking about this as a strictly object-oriented problem and want to use classic object-oriented constructs. So no special keywords like, for example, yield. And I'm not trying to take away or diminish the power of yield, because clearly that's an awesome keyword. Anyways, okay, so this we can't do, and I hope you see the reason. The point is we don't want to build up this intermediate collection, right? So how can we do this? So actually, let me undo backwards. I'll just undo backwards until we are, let's see, here, right? Actually, no, actually, let's go backwards even more. Let's go back here, okay? Until we had, where we just say run here, and then we have a side effect inside of run where it's console writing to line, right? Or it's writing, sorry, I'm too tired. It's writing to the console, right, as a side effect. Actually, that's an interesting way of thinking about it, like a side effect. In this case, the side effect is desired. We want the side effect as the program is running. We don't want to accumulate all of the side effects into one big blob and then write that side effect in the end. We want it to sort of occur as we are executing this particular code. But anyways, so what we want to do is we want to get this console write line out. So one way of thinking about the strategy pattern is that, I mean, there's that interesting statement, I can't remember who originally said it, but that the object-oriented design patterns are in some way just a way of making up for the shortcomings of object-oriented languages, right? So in an object-oriented language, you can't pass a function as an argument. Functions are not first-class citizens, right? As in functional programming, where you can pass a function. Now, of course, yeah, I know C# and Java and all that stuff have things such as delegates, and you can pass actions, and you can pass, like, I guess func is a type or something like that. I mean, clearly there are ways of doing it. Clearly. The point is not that, right? The point is not that C#, for example, can't pass around functions. C# can pass around functions. The point is that the object-oriented paradigm, the core key concepts of the object-oriented paradigm, does not support the idea natively of passing around a function. Now, so I would not say, for example, that C# is an object-oriented language. I would say that C# is a object-oriented heavy language, or something along that line, right? Something along those lines, because it's sort of mainly based around the object-oriented paradigm. But nowadays, you have, LINQ, right? Like, you essentially have many of the functional programming constructs in C#, right? So it's a mix. Like, they're taking bits from here and there. Now, okay, I don't want to get into this whole like language discussion and all that, but in my mind, if I just say like 2 cents about it, like in my mind, the fewer constructs you can use while still like properly maintaining sanity. I'm not saying like we should use some of these silly languages that like use almost no special keywords, but like in, for example, functional programming, you have fewer key constructs than when you are sort of using the whole plethora of C# or the whole plethora of constructs of C#. My understanding is that you have fewer constructs, but you still have the same power, right? And you can maintain sanity. So I think that's a good thing. Like Occam's razor, right? Like if there is a simpler solution, if there are two solutions and one is simpler, then clearly the simpler one is the better one. So a language introducing a multitude of different ways of doing it just because people want to do it in a multitude of different ways, I don't think it's necessarily a good thing, right? Long term. But anyways, now we're totally off topic. Where am I going? What I wanted to say is that a language such as C#, if you use the sort of key object-oriented constructs, does not support the idea of passing around a function. So the reason I'm saying that is that if you think about this, console.writeLine, this is really the problematic part, right? This is not necessarily the problematic part. We know that we want to have some kind of side effect, but we don't know what side effect we want. And we know that the side effect is based on result. It's somehow based on the result that we build up as we run the simulation. And then this side effect, so essentially what we want to choose at runtime is the side effect, right? And so if I just do this, I'll remove this and I'll say f here. Now f represents a function. In a functional language, you would just do something like that. You would pass f as input, and then you would delegate to f. You would run f on the output, right? And that would be that, right? And in some sense, that is exactly the strategy pattern, right? The strategy pattern exists so that we can pass around functions. That's the strategy pattern. And this is like, again, hopefully then you can see why people are arguing that design patterns are overcoming the flaws or the shortcomings of object-oriented languages, right? Because it's kind of obvious that it's a useful idea to be able to pass around functions. But anyways, okay, let's get to it. So in lieu of this, right? Instead, since we can't say this, since we can't pass f, whoa, what am I doing now? Since we can't pass f, what are we gonna do, right? We can't pass f here, and we have this console.writeLine here, and we want to get rid of that. Well, what we need to do is that we need to wrap that in a class. So check this out. What we do is this: we take it in the constructor. So public simulation, and then we take let's say a writer. Let's call it writer, and then we'll say this dot writer equals this writer that we were passed in, right? And so again, like, think about this. If this was a functional language, this is essentially the function that we're passing in. We're saying the writer function, right? We're passing in a function that writes that can do some kind of writing. And then we'll save that in here, and we'll pretend we have a writer type, and we'll say writer here we just declare the existence of that writer. And actually, let's stick with that. And then instead of saying console.writeLine here, what we do is essentially that we just say this.writer, take the writer that I have and call the write method on that, right? So instead of saying call the function f and pass it result, right? Invoke f with f or whatever. I'm super confused. Okay, pass result to f, right? we can't do that. We can't pass in f, but we can pass in a class that has a function that we can call, right? So instead of just calling write on result, like assuming write was this function that was passed in, what we do is we call this.writer, which is a class that has a function write, and pass that result. So then we need to have, of course, we need to have an interface which is called writer, for example. Or, sorry, not for example. It needs to be called writer because we said that the interface here is writer. Maybe I should say iWriter because C# tends to use this sort of I to denote that things are interfaces. I mean, never mind. We'll just call it writer, right? And then there are, I don't know, I mean, I can't remember, but there's somebody who's been critiquing the usage of I, like as in that it creates unnecessary bloat, and I guess like the point is something like, since you should always couple to abstractions anyway, you should always assume that the type is an abstraction. But whatever, that's a side note. Let's not use the I notation now. So what is the signature of this method? I don't need to specify that it's public, but what it needs to, I mean, at least it needs to be called write, and it needs to be passed something which is this result, right? Which is of the same type as this result, and that's essentially a string. So so a writer is a class which has a function that is called write, takes a string and returns nothing, right? Because presumably it's something that performs some kind of side effect. It's some kind of writer that writes somewhere, whether that writing is to memory, right? It could be to memory, or it could be to file, or it could be to screen, or it could be like any of these things, okay? Because what we could have then is that we could have okay, a screen writer. Actually, let me call it a console writer, which implements the interface writer, and it has an it has a function which is public and it returns nothing, and it's called write because it implements the interface write, and that takes a string, and we're going to call that result. And then we're going to have some implementation of that. And what is that implementation? Well, essentially, actually, now I removed it from here. But it essentially, the implementation is what was here, right? Line result, right? Because, like, again, every problem in computer science can be solved with another layer of indirection. What we've created now is another layer of indirection. We've said, instead of directly calling console.writeLine, what we're going to do is that we're going to call the function write on the instance, on an instance of type writer, which was passed to the simulation over here as an argument to the constructor, and then set as an instance variable here. We're gonna call that, and if that happens to be, for example, a console writer, which it could be because that is of type writer, and what we are expecting is something of type writer, then what's going to happen is that we're going to call this original line that we were now extracting, right? This original line that we were creating a level of indirection around, I guess you could say, or something like that, right? Instead of doing this thing directly, we're going via a writer, so that this writer could be varied, so that it could be any other writer, right? And again, think about the definition of strategy pattern. Something like it defines a family of algorithm and allows you to, at runtime, vary between them. So the family of algorithms is now the writer family. Anything that's a writer is part of this family that could be used as part of this example of a strategy pattern. And then the console writer here is one instance. It's one member of this family. So the console writer could be exchanged for any other old writer that implements the interface writer, and then you could take that other writer and pass it to the simulation. Before we create another writer, let's make sure this runs, right? Because of course this doesn't run now. Let's check out the compiler error so you can see. I mean, oh, okay, sorry, this is a syntax error. 25. What am I? Oh, sorry. Of course, I need to give this a name. That's all. Result. Right? So maybe a bit indicative. Whoops. Okay, like so. Let's compile. Type simulation. Yeah, so this is the error I was expecting, right? The type simulation does not contain a constructor that takes 0 arguments. Line 5. Okay, 5 here, right? Because obviously it doesn't, because we changed it. We now said, in order for you to be able to construct a simulation, right? Like the idea of instantiating a simulation requires provision of requires providing a writer. You need to provide something that satisfies the writer interface. So first we need to create a writer, right? Let's say, okay, we have something of type writer. Let me just call it writer. We have something of type writer. Anyways, word jokes. We have something of type writer. Let's call it writer, and we're gonna instantiate essentially a new console writer. Okay, new console writer, and we'll pass this writer to simulation. How about we compile now? That's fine, right? Because that's all we needed. That's essentially like all we've changed. And let's just run that, right? Let's run and see what happens. Now we get tails here. So we're back to having a working implementation. Let's run again. Heads, tails, tails, heads. Yeah, so it seems kind of random, right? It seems to be working. So that's pretty cool. And now, okay, what if we go back to this thing? What if we say that actually running does not just involve running a single time, it involves running 10 times. So we'll go to, we'll create this for loop again, and then we'll just put this stuff that we had before within the for loop. Notice that it's still a void method, so we're not returning anything, and we are essentially just doing these two things within the for loop. So we're just essentially doing this thing multiple times, which means that we are invoking the write method on the same writer without passing another writer, right? Because we have the simulation the simulation class, which when instantiated will be passed a writer, an instance of something of type writer. And that thing, the write method of that thing, will be invoked every time we have a result, which we have computed here, which we will do 10 times, right? Let's look at that. So we compile again, and then let's run. And that works, right? Tails, heads, tails, heads, heads, tails, heads, heads, right? And think about it. We are not constructing a temporary list and we're not putting that list in memory, right? We're not actually building up some kind of list. We are using strategy pattern to delegate to something which has a side effect. But I mean, of course, like from a, let's say, functional programming perspective, this is of course still not elegant, right? And from a perspective of using yield, this is not elegant, right? Because we still have a side effect, right? We still have a side effect which is buried somewhere deep in the application code because we've passed in something that at any point in time can produce a side effect. So I'm referring to the writer, right? Because this writer is the thing that's causing side effects, and that thing can be passed deep down into the depths of a system, and it will then cause side effects. And it's not necessarily obvious that that's wanted, right? But like it's still a fairly, I would say it's a fairly obvious and well encapsulated way of having a side effect, right? Like scattering your side effects all over, not a good thing, right? So for example, this random thing we might want to start to think about, but not a good thing. Okay, now we're on a sidetrack, right? But encapsulating your side effects into something like a writer, I would not say the end of the world, right? Because it's obvious that this is like a sink, right? It's like it's something that you push out data into, and it's not going to affect any of the other parts of the application. You're just pushing data out into that. And then you're not scattering that sort of mutating code all over the place. You are just putting that mutating code within your writer. But anyways, okay, sorry, this is a completely different discussion. Let's get back to the strategy pattern. So let me try to, maybe I should try to wrap this up. But before we do so, let's actually introduce another writer, right? So now we have this console writer, which is of type writer, right? And we can use it in the simulation. But let's construct another one. Let's say that we have a okay, sorry, this is of course where we wanted to go. Let's say that we have a file writer, which is of type writer. We're not actually gonna implement this properly because then I have to figure out how to write to files, and we're gonna have to look at the file system and all of that stuff. So it's unnecessarily complicated. But it has, since it implements the same interface, I mean it implements writer, it also needs to have a public, it needs to have a public method that returns nothing and is called write, and takes a string which we will conveniently call result here as well. Now that thing would write the result to file, right? But wait, which file? Okay, let's use the constructor. Public file writer, string path, let's say, I mean path to file, and then this path equals path. Okay, and then we have a string here. We have a private string which is the path, and then that's that's the path to the file. And then when we write the result. So we write the actually like the string, the contents of the string result to the file at path. Well, I mean at the path of the instance variable path. I mean, you get the point, right? I mean, we write results, maybe this I should say, to path. That makes more sense, right? We write whatever we are passed here, and it's not actually called results, it's called result. We write that to path, right? I mean, how simple could it get? And then instead of instantiating this console writer, let me just say, okay, first, these two can exist simultaneously in the application without actually colliding, because they're just classes that implement some particular interface without saying that now I want to use the file writer mechanism, right? Like this is like miles away from doing something like switching on and off from a Boolean where you say write to file, yes or no, for example. Like this is like a million times better, right? Don't do that, like the whole write to file, yes or no. Now these two can exist, right? I compile and no problem, right? Essentially all it's saying is that, okay, the private field path is assigned, but its value is never used, because here in file writer we have this path variable that we're assigning here. And I mean, essentially that's because this has no implementation, right? If we actually supply this implementation, then of course this error would go away. Or sorry, not this error, but this warning that what we're doing is pointless. But now we could just switch our writer. So instead of having a console writer, right, we could just switch this and say, well, I have a file writer, and I want to write to the file, let's say output.csv, for example, as we mentioned in the beginning. Like let's say we're constructing a CSV file, or let's say I'm txt maybe, right? I'll just save this, compile, that compiles, we run it, we get nothing, right? Because no longer are we printing to the console. No longer are we using the console writer, right? Because if we use the console writer, compile, run, then we are writing to console. But if we are using the file writer, then we are writing to file. Actually, now we are not writing to file, right? But I mean, we are running this particular implementation. So like, let's say console write line. Let's just as a sort of debugging, as an example, just to see that we're actually hitting this particular code path. Writing, let's say result to path. Right? Compile, run. Yeah, so it's writing heads to output.txt. Then it's writing tails to output.txt, writing tails to output.txt, and so forth, right? And so the way I used this, for example, in that other code base, was that I had a CSV writer. So I had something that when it received the first piece of data, it looked at the data and determined what the headers of the CSV file were, wrote that to the CSV file, and then as soon as it just got more data, it kept on sort of dumping that data to the CSV file. But you can do all kinds of complex things, and here's what I'm thinking. Let me know what you think about this in the comments, but I think maybe this serves as a good starting point for discussing the different design patterns. So I think we're going to return to maybe not exactly this code base, but at least we're going to start from, or we're going to return to this particular example, right? This idea of running a simulation, and we're going to try to incorporate design patterns. And I mean, it's kind of funny because then we're sort of letting design patterns guide the design of our system rather than our requirements. But that's because we don't have requirements, so it's completely fictive, right? But rather, hopefully, what you can see is how design patterns can open up new avenues of abstraction, or rather how it can make your code base afford particular types of changes very, very cheaply, how it can make particular kinds of change requests extremely cheap, right? Because this is the way this particular thing that we've done now, this I would argue is one way of making sure that the change of where do I output this data, that we just made it extremely cheap to change that or decision, I guess, right? Or change where we actually want to write stuff. So what I wanted to say is essentially, yeah, I think we're going to return to this sort of simulation example and try to incorporate lots of different patterns, hopefully at the same time. Let me know what you think about that in the comments. And yeah, I think that might be an interesting way to talk about the different patterns. But anyways, the reason I'm saying that is that now we have a file writer. We can switch between a file writer and a console writer, for example. But you might also think about sort of composite writers, or maybe not composite maybe composite is a bad word because of composite pattern. But if I have a CSV writer, maybe I first want to sort of pre-process the data so that it fits CSV format, and then I want to output that data to screen, right? So then it's like a combination of a CSV formatter and a screen writer. But I should be allowed to do sort of a CSV formatting and then writing that to file. Right? So that would be a very flexible way of separating the idea of sort of formatting and the idea of where you print the data. But maybe these don't necessarily have to be different things. Like you could also think about, so if you've watched the other whiteboard series, or if you're familiar with patterns from before, we could think about this as, for example, the decorator, probably. I mean, I'm just or off the top of my head, or maybe was that like proxy? But probably like decorator would make sense. We're saying like maybe you would decorate a file writer with a CSV formatter. So first it formats in CSV format and then puts it into and then delegates downwards to the file writer, which then writes the file. So first we decorate it so that we first reformat the output in CSV format, and then we punch it downwards into the file writer or the screenwriter or whatever writer we happen to have. That's one way of doing it, right? Another way of, now I just lost my train of thought because I was starting to think about a different thing, but there are other ways of approaching it that are probably valid as well. Actually, I can't remember this. Hopefully it will come back to me. Meanwhile, while I'm thinking about that, let's just jump in here and say that, of course, I mean, clearly this looks a bit messy, so you could just inline this and say that you have a screen writer here. This kind of bugged me, right? And then, I mean, you could just do this probably, and that would be completely fine, I guess, right? Let's remove this and remove this, and let's see, does that compile? Oh, sorry, it's not actually called screenwriter, it's called console writer. Yeah, that compiles, and then we can run that still, right? So that's pretty dense. And then, of course, I mean, sorry, now I just hard coded this 10 and all of that stuff. So of course, clearly what you would do if you had a simulation is probably something like you would pass, okay, I want to have 10 runs, and I want to have seed my randomizer with the number 1, for example. So then the simulation would take more arguments here. The simulation class would take more arguments. So you would have something like let's say int n for the number of times you want to run the simulation, and then int seed for the seed that you want to seed the randomizer with. Then we say this dot n equals n, this dot seed equals seed, and then let's just line these up. And then we need to have an int n, we need to declare that, and we need to declare a seed. Yeah, this looks a bit funky. Let's put these here, and then let's not instantiate the randomizer here. Let's instead instantiate the randomizer here. So we say this dot rnd is equal to a new random, was it random? Yeah, new random, and I'll pass the seed. And actually, since I passed the seed immediately, we maybe don't even need to save the seed, so we don't need that variable. And then here, instead of going up to 10, we just go to n, right? So that would probably make more sense. I'm just sort of cleaning up, right? We're still running 10 times, but now we could change it and say, let's run 100 times, right? Compile, run. Yeah, now we get 100 as output, right? Or like 100. Yeah, I don't want to do 100,000 because probably like my screen capturing software will not, my computer will not manage doing all of these things at the same time. Pretty sad. Anyways, but yeah, and then you can see like if we would go up to, whoops, now I'm recording a macro. Accidental. Did I cancel it? Record, cancel. Okay, cool. So like if we go up to these huge numbers, clearly it would make sense to not have a console writer, but it would make sense to have like a file writer that we would write to intermediately, or like as we are running the simulation. Now I finally remember what I wanted to say before. What I wanted to say before is that we could use, I think maybe this would actually count as proxy pattern as well. So another way of thinking about a decorator, or another decorator that we could create, is something like a batcher. So if you think about it, performance-wise, if you have like 1 million runs that you want to run, you want to run your simulation 1 million times. Okay, you want to write to file intermediately, like all the time, right? or I mean, essentially, you don't want to wait and write the file just in the end. You want to write sometimes in between. The question is, it's a trade-off, right? Because writing to the disk is also slow. And if you're in a sort of synchronous environment, if you're synchronously writing to file, then you're like the computation has to stop because you're writing to file. So you need to finish writing to file. So if any run of the simulation, like just one lap, let's say one world, one particular sample is very quick, then it might not make sense to write every time. So then maybe you want to sort of find a good balance, and you say something like, well, okay, for every 100 times I want to write a file. So you'll collect up 100 input items, and then you'll flush those to file, right? And this is exactly what I did in this other Ruby code, right? So like then you would have another writer, or like let's say you would have a wrapper, you would have a decorator around one of these writers that collects data in memory, like okay, 1 run, 2 runs, 3 runs, 4 runs, and so forth, like 99 runs, and then you have 100 runs, and they're like, okay, I have 100 runs, flush that to the next writer, pass that to the next writer, and reset all my data. And then the next writer then maybe is the file writer. So then you would flush that to file, right? And hopefully you can see how we're sort of, it's actually, as you get going with these things, it's absolutely trivial to build up these things. Of course, immediately it's not, right? Because you have to get used with working with these different abstractions and sort of immediately putting yourself in that state of mind. I'm not trying to be rude in any way by saying that it's trivial. I'm rather trying to say that as you get comfortable with that, you'll realize that it's absolutely trivial, and people who are complaining about over abstraction are pretty silly, right? It's pretty silly to say that this sort of using that kind of decorator where you would you have a throttling was the word I was looking for, right? That's essentially the mechanism we're talking about. You throttle a bunch of output. So it's like in some sense, metaphorically, it's like we have a stream. So you have a stream of output data, and then you have a throttler in between that throttles and says, okay, well, first I need to collect a bunch of data, and then I'll flush all of that to the next processor in this pipeline that processes this stream. So like I'll throttle all of this data, that this simulation output data that's coming in. Now I have enough, I'll flush it, I'll pass it to the next one, and then that thing does whatever that does, but maybe it writes it to file, maybe it writes it to screen, or maybe it sends it off the internet, or whatever, right? And yeah, I mean, it's I don't think, maybe not anymore, maybe people aren't complaining about that kind of stuff anymore, but hopefully, like, try it out and don't listen to people who say that that's over abstraction. That's not over abstraction. That's an extremely cheap investment with the return of making your code extremely, like, massively more easy to change and massively more easy to reason about, because suddenly you have composable components. But anyway, sorry, now I went way beyond by talking about decorator pattern, for example. And also, if you think about it, if we now start to talk about streams, then we could also talk about observer pattern. And actually, the next video will be about observer pattern. So I think what we're going to do is that we're going to do something like, we're going to use exactly this example, but we're going to say, what if you want to write to screen at the same time as that as you are writing to file, not as in this like parallel at the same time, but like now we have one simulation, and that simulation is injected with a writing strategy, this console writer. But what if we want to have both a console writer and a file writer, right? So either you could have a split writer, which splits, right? Like that would be sort of a stream way of thinking about it. But another stream way of thinking about it would be to use observer pattern. And then we would say that the simulation is observable, and whenever it emits data, all of the observers can consume that data. And then that's also sort of a stream way of thinking about it. Anyways, now I'm way off topic and probably way over time. So let's wrap this up. Hopefully this was a more useful example, because I guess you can see how this is, again, like applicable everywhere. Like, again, think about it this way. If there's ever something that you feel is kind of hard-coded, you can almost, like in a place where you don't think it should be hard-coded, you can almost always dependency inject that thing. And if that thing is a function or a procedure or something that's being carried out, regardless of whether you wrote that thing that's being carried out yourself, or whether it's something like from the system, like something from the .NET library, like what we used here, the console write line, you can always encapsulate that. You can always take that thing and put it inside a class and give that class a name, and then delegate to the method that executes that particular piece of logic. And I mean, again, don't worry about extracting tiny classes. That's fantastic, right? I mean, just think about this. We have the console writer here is essentially just all this craft around the idea of writing a string to console. Like it feels completely stupid, but it's not completely stupid, right? Maybe the stupid part is that doing this whole thing should require less syntax in the language, but that's C#'s fault, right? That's not our fault. Of course you should be doing this kind of thing because this gives you the option to switch between console writing line or doing something completely else, right? Because you might have the intuition that at this particular point, it's completely not obvious that I only want to write a console, right? And I don't yet know the cost of hard coding this idea of writing to console. Anyways, now I should really wrap this up. Hopefully this makes sense. Shoot any questions if you have them in the comments, and let me know if this example was useful, and let me know if you think we should continue talking about simulations as sort of an example application where we can put design patterns, that we can put design patterns into, or we can use design patterns. Anyways, thank you super much for watching. Glad to have you here. Remember to subscribe so that you won't miss any of the upcoming videos. Hit the like button if you appreciated the video, and I will see you in the next one. Thanks a lot for watching.